Hello everyone. Here is our assignment of overfitting and underfitting in polynomial regression. And here is the guidance Akshata AMS ma'am, and assistant professor of AML at JM University. And here are the team members: Anjan SR, SK Karthik, Vaibhav Patil, Santosh, and me, and Venkatesh. Here is the introduction of our data set. Here is the objective. Analyze the overfitting and underfitting in polynomial regression, demonstrating bias variance, trade-off, and regularization. And the dataset is a California housing sky learning, 20,000 some samples and 8 features, and Medellin and house age via rooms. Target is median house value, and median house value is a 1 lakh dollar, and pre-processing up to 80 by 20 train validation splitted into more samples, and standard and scaling up for a numerical stability. And methodology is polynomial regression decreases 258, evaluate a MSc, apply ridge lasso regression. And next slide is continued by SK Karthik.
Next one is the polynomial regression result, where the models polynomial regression with degree 2, 5, and 10 are used. Where for degree 2, the training MSC gets a 0.525, and for validation it uses 0.544. Like that, for 5, 0.432 and 0.460. For 10, it is 0.125 and 0.620. These are the training and validation values for the degrees 2, 5, 10 in a polynomial regression, where we uh, trained a polynomial regression with our real-time data set. And next in the observation, we see that training MSc decreases with the degree, like better fit. Next is the validation MSc, where U-shaped curve for a minimum at degree 5 will come. Next slide will be explained by Vaibhav.
State how model complexity affects bias, variance, and total error. This concept is known as error decomposition. In error decomposition, we have the formula called total error is equal to bias square plus variance plus uh, uh, ir- irreducible error. Bias square means error due to oversimplifying the model. Variance come from error due to too much of sensitivity to training data that makes the model overfitting. Uh, reducible error means noise in the data that cannot be avoided. In degree 2, the degree 2 model has high bias, meaning it is too simple. Both training and validation errors are high, showing it shows underfitting. At degree 5, the model achieves the best balance. The validation error is the lowest, which means it generalizes well without overfitting. The degree 10 model has very low bias but very high variance. It it memorizes the training data instead of learning patterns. This is called overfitting. So overall, degree 5 gives the best trade-off between bias and variance. It generalizes well, making it most suitable model among the three. The next slides will be continued by Anjan.
So the regularization. It is a rigid lasso to reduce overfitting. The model is used for training and validation purpose. We are finding the rigid lasso reduced validation method for analyzing large coefficients. Lower variance improves generalization. In conclusion, degree 5 validates bias variance, regularization enhances high degree model performance. Now it is continued by Santosh.
Underfitting in degree 2, I bias with training MSc 0.525 and validation MSc 0.544 to simple for normal non-linear patterns. Overfitting in degree 10, low training MSc 0.125, high validation MSc 0.620, first noise, poor generalization. So balanced degree 5, lowest validation MSc 0.460, optimal complexity for generalization. regularization benefit ridge 0.330 and lesser 0.340, reduce validation MSE, lowering variance, model selection insight, emphasize evaluating complexity and using regularization for better generalization. Thank you.
This is our code for the AML, where we train it as a data set for like a California housing prices for a experiment. Where it first we in under polynomial regression we got the result for degree 2, 5 and 10. It is 0.69 and 0.73 for validation. Like that we got a validation training and a validation values for 2, 5 and 10. Next is the bias variance analysis, where the degree 2 is the, comes under underfitting and degree 5 is a good trade-off. For 10, it is a overfitting, where it gives a high bias, balanced bias, and a low bias variance. Next one is the regularization error. We will get a polynomial degree for where the training value is 0.67. For ridge regression, we got the 0.67, and the last also we got 0.67. And for validation, 0.69 is common nearly to everything. Here the final summary is that degree 2 is the underfitting and degree 10 is the overfitting. And degree 5 is the best bias variance trade-off with the ridge and lasso, where it reduces the reduced overfitting and improved validation error. For this, there are some charts here. First chart is the training versus validation error, where it gives the values of 0.69 for training error for and validation error 0.70. Like that. Next, for the validation error with and without the regularization, we got 0.69 for a polynomial degree, and 0.69 for ridge, and for NASA also we got a 0.69. Thank you.